All right, friends and neighbors, welcome back to another CCNA video. We are doing Volume 2, Chapter 13, LAN Architecture. So this is kind of cool. We're going to see how things are all put together when we're talking about campus area networks. So in this video, of course, we have the key topics. Our exam section this time is describe the characteristics of network topology architectures, most notably our 2-tier and 3-tier. We're going to spend a little bit of time talking about SOHO networks as well. And then we're going to talk about the concepts of power over Ethernet, and that is under the umbrella of physical interfaces and cabling types. And then the do I know this already questions. So we'll go over some LAN design terms. We'll talk through a couple of topology diagrams, and then we'll talk about some components. So it turns out that we've got a bunch of base topologies, right? Bus, star, shared, unshared. And we're going to find out that our topologies that are larger actually have components of several of these. And then, of course, our big topics are going to be the 2-tier or collapsed core LAN topology and the 3-tier with a core LAN topology. I will define all of those. What do the components mean? We'll talk a little bit about SOHO, as I mentioned, and then all the PoE standards. So there we go. And then we'll talk through, what happens when a device powers up and needs some power over Ethernet. Now, to get started, at this point, there's a whole bunch of things that you know about, sort of networks, right? We know about Ethernet networks. We've talked about Ethernet and how it operates. We've talked about switches and how they operate. We've talked about cabling and the cable plant, duplex and speed settings for when a node connects. We know that there's this negotiation stage that a node goes through to see whether or not it can do 10, 100, or 1000 base T gig, right? Then are we going to do full duplex or half duplex? We also know in a layer 2 topology, if we have loops, we've got to have something that saves us from ourselves, and that's spanning tree and rapid spanning tree. We also know that we can ignore spanning tree on a couple of links when we want to double up or triple up or quadruple up the capacity between links. And we do that with ether channels or port groups. And then a couple of videos ago, we did dynamic ARP inspection and DHCP snooping to help do some layer 2 security. So that's all stuff that we've sort of covered, right? What we haven't talked too much about is how to put all of those components together in a larger architecture and a larger topology. So there's some design considerations that we worry about, some very common architectures. They've emerged as the ones that everybody uses. And then, we'll talk a little bit about what links or how many links we put between different layers of our model. And again, 2-tier, 3-tier, and SOHO. So that's what we're going to do. Now, some general ideas about our architectures. Well, a campus LAN, so if we start thinking about what's a local area network, and we could start really low level and we could say, well, a local area network is all the nodes that might share a layer 2 substrate. We might say that they all share the same IPv4 or IPv6 address space. We can say that. But when we start growing things, then we say, well, what would you consider a campus? Now, most people consider a campus when they think about colleges or universities, but a campus is really just a group of buildings that are together. And so you can have small campuses and large campuses. And so a campus LAN then is a LAN that's created to support devices in a building or in a collection of buildings that are close proximity to each other. So when you're putting all that together, you kind of say, all right, well, what kind of Ethernet are we going to do? What kind of cabling are we going to do? Are we going to do fiber? Are we going to do some kind of twisted pair? So it's very common to do twisted pair inside a building, right? And then do fiber between buildings. But if the buildings are close enough, you might actually do twisted pair between them as well. What devices and applications need to be supported? So do you have things that require high speed? Do you have a bunch of servers? What applications are your users using that need to be supported as well? Is this an upgrade or is this brand new? So is this a brownfield build or is this a greenfield build? So if you've got gear already in place, do you want to buy the same kind of thing? Do you want to buy upgraded things? Do we all have the same set of features across all of those devices? And then you've got all the connections to your nodes. And do we want to do inter-switch connections? Well, we do, but what are they going to be like? How many are we going to do? And what kinds of connections are we going to have? And then there's a dollar value associated with all of this. Cost will be one of our big limiters. When you look at a network device, one of the common dollar values that you see is the cost per port. And the higher the speed, the more capacity in the ports, right, the higher the cost is going to be. What kind of chassis are you going to build? How many ports are you going to burn with just connections to other switches? So these are all things that factor in. And then you've got your design choices. How are you going to put this together in your campus, right? Are we going to use a 2-tier or a 3-tier design? And then, size is a huge question. If you're dealing with a really small campus or a really small business or even your own home, of course, we call that a SOHO or small office home office topology. Okay, so this is a typical large campus design. This is called 2-tier. It's also called the collapsed core, and that's because it doesn't have a core. And that means that these switches at the top here, they're actually going to be serving the function of the core switches. So in a design like this, right, now remember that we're talking about 1, 2, 3 buildings. So we might have up to 1,000 PCs and a whole bunch of switches. And in this case, the example in the book is that they're 25 port switches. And what that means is that you've got enough ports to service your nodes, but then you also have ports that are going upstream, right, to the next layer up. Now, switches and routers live at our various layers of our design. So you can see here that we've got the access layer and the distribution layer. In a 2-tier design, there's really no core network or core layer. Or we might say that the distribution layer and the core layer are doing, they're doing the work is all being done at that one layer. Now, as it makes sense, right, the access switches here support connections to the network. That's how you access the network. This is also where your access points, right, your wireless access points might be, and all your nodes here. So in this diagram, we can see we've got about 40 access switches, each with about 25 ports. So that's where the support for 1,000 PCs comes in, about. And then these connect upwards to our distribution switches. So this also means that the lower level switches, these ones at the access layer, they have a different job. They're managing access to the network for all of these nodes. Now the distribution switches, they connect to each other, and their main role might be things like access control, firewalling, AAA, authentication, authorization, and accounting, right? They might be doing that role, but they're also involved in redundancy. So we can see a couple of examples here. We can see that we've got some ether channels here or some port channels. We can also see that the switches are connected to more than one other switch. We try to anyway, right? So A1 might have just multiple connections up here, but A2, we can see that we've got a bunch of connections here. Now, importantly, every switch is not connected to every other switch, and we'll talk about that here in a second as well. Now, what happens if, this D1 switch right here goes down? Well, we're cross-connected so that everybody can theoretically get out through the other D1 or distribution layer switches. And then very commonly you'll have a couple of connections to the WAN, again for redundancy or maybe even load balancing. So most designs, a couple of uplinks from different switches to the next layer up. Now uplinks are a port that you're actually burning, right? So if I said that this A1 down here has 24 nodes connected to it, and then I've got these uplinks. Well, these uplinks might be fiber, they might be unshielded twisted pair, but they might be higher speed modules, right? If these are all supporting whatever nodes are going to be connected, your uplink ports, you're going to want your higher speed there, and again, they might be fiber. So let's get some terminology here. Star, the central node, is connected to sort of spokes. So this is what we might see at our access layer, and that's actually a question in the chapter. So if we imagine all of these outer nodes here, or outer vertices, as stations or PCs, and the central node here is a switch, well, we got a star-wired topology. Now, our next one here is what we call a full mesh topology. And what this means is that everybody is connected to everybody else. Now, this is an extremely expensive topology to build because In this topology here, there are no nodes. These are just switches connected to every other switch. In this 6-switch topology, right, if I imagine that I'm connecting to everywhere else, and I take this first switch right here, how many switches am I connected to? 5. Well, the next switch down, because we already have one down here, this switch has to connect or have 4 unique connections, and the next one has to have 3 unique connections. So in all told, you would burn 30 ports and 15 links just to establish our full mesh topology. Now the formula that works out with this is n times n minus 1 over 2. So if you think about how this works, we've got 6 nodes here, and so we go n, which is 6, then n minus 1 is 5, that's 30, divide the whole thing by 2, that's where the 15 comes from, but you could actually, in a small topology, count how many it would be. So this is extraordinarily expensive, both in terms of the number of ports that you're going to use up, the fiber strands or the UTP strands that you're going to use up, but also you've spent money on these switches, and you're using the ports for just interconnectivity. And most folks would say this is entirely excessive. So what we usually do is something called a partial mesh. We figure out the parts of the network that require extra redundancy, and then we say, okay, those are the places where we're going to burn extra ports to get an extra connection. And so the connection between the access layer and the distribution layer is very commonly a partial mesh. Now there's hybrid designs where you have a mix, where you got partial mesh going down to star. And so if we think of the access layer as a star wired topology, but then the access to the distribution layer is a partial mesh, well, there you go. So you wind up with something like an extended star or a hybrid topology. Now, if we're getting a little bit bigger, or we've got a little bit more concerns in terms of performance, utilization, speed, things of that sort, then we might go with a 3-tier campus design. This is also the traditional design model. And what we're adding here is the core. Now, if you have a bunch of buildings, right, you could theoretically just interconnect each building's distribution layer to every other building. So you could do that with either a full or partial mesh. But if you're interested in speed, and in particular where you're aggregating things together, then what you want, or maybe a better way to go, is to add that core layer, because the core switches are all about performance. The key there is packets or frames per second. We want to move things out. So where the distribution layer might have things like AAA, the core layer is all about forwarding packets and frames. Now, I suppose it's worth mentioning at this point that historically, many of these designs come out of the telephony networks. And one of the names that we have for these kinds of network is called a CLOS topology, a CLOS. Now, there are variations on a theme, but that's sort of the genealogy of all of these designs. Okay, small office, home office networks, or SOHO networks, not the location, but the type. They're not the same as the campus or enterprise network, right? They're smaller in terms of size. So fewer workers, fewer devices, lighter capacity needs, sort of standard set of applications. And the central node might even be a wireless home gateway. So if you think about what this little device has in terms of capability, right? Your wireless home gateway is a router. It's a switch. It's an access point. It does sort of entry-level firewalling. And then it's got a DHCP server built in. So that's a lot of capability built into a relatively inexpensive device. So again, one of the questions in the chapter is what sort of equipment would characterize a SOHO network? And that is that all of the capability is centralized in one device. Now, this doesn't mean that you can't have dedicated routers or switches, but usually we don't have that level of expense. If you think about, a small doctor's office or a small lawyer's office, they're not going to have a huge network capacity built in. We just want good internet connectivity and then service for all of our machines. And we might do a lot of cloud applications. Now, there are a couple of chapter reminders here that when you're dealing with Ethernet or wireless, right, These are the IEEE 802.3 and 802.11 standards. And so all of the rules for those protocols can be found in those standards. The minute we move to layer 3 and we start talking about IPv4, IPv6, ARP, ICMP, TCP, UDP, these are all the Internet Engineering Task Force RFCs. So let's talk a little power over Ethernet. If you're going to throw up a wireless network, right, historically what we would have had to do is find outlets for all of those access points. But we don't have a lot of outlets in the ceiling. So what we did instead was we plugged in a power injector, like this one here, into the wall, and then we ran the connection from the switch into one of them and the connection to the device out of the other one. And what this power injector did was run power to the Ethernet line. And if the device was capable of doing power over Ethernet, this is how we would do it. But that also meant that you were using an awful lot of outlets for these power injectors or bricks. They're also called power sourcing equipment. So imagine the number of outlets that you would have to use if you were going to supply power to all of your access points or all of your voice over IP phones in this way. So today we get rid of this entirely. We don't like the bricks anymore. We do power over Ethernet right from the switch ports out to the devices. Now there are some limitations, right? There's a distance limitation. There are the power level that you can provide. But the IEEE standards are where we're going to find all of these details with regard to power over Ethernet. And because it's power over Ethernet, they all begin with 802.3. Now to begin with, any node that needs power or can receive power via power over Ethernet is going to come up and signal via auto negotiation, A, its need for power, and B, what class of device it actually is. Now it's really important that a PoE provider, a power sourcing equipment, right, a switch in this case, doesn't automatically start pumping out power. Because if you hook up a device that doesn't accept power over Ethernet, then you could damage that interface or damage the device. So it's really important that the device signal what it wants, and they have a conversation about how much power is needed and also changes over time. So this starts with auto negotiation, which is also how we get the speed of the link. It's also how we get whether or not we're going to do full duplex or not. And then we can extend that with something like our layer 2 management protocols, CDP or LLDP. Now, how does power actually get to the various devices? Well, it's usually over 2-pair or 4-pair. The 2-pair power is the pairs that are not being used by the transmit and receive lines on Ethernet. So Ethernet uses 1, 2, 3, and 6. Pins 4 and 5 and 7 and 8 can be used for power without worrying about affecting Ethernet. The more advanced standards actually figured out a way to use 4 pairs for power. Now, one of the cautions here is that if you've got a switch, say you got a 24-port switch, could you hook up 24 access points that all require power? Maybe. Now, a switch that is power over Ethernet enabled, sometimes all of the ports are power over Ethernet capable. Sometimes a collection of them are power over Ethernet enabled. And you have to be aware that you don't want to put your switch in a power deficit. And what that means is that the devices are asking for more power than the switch can actually provide. So here's some more details on power over Ethernet. Above me, we have the different standards, Cisco inline power, and then power over Ethernet plus, universal power over Ethernet, and universal power over Ethernet plus. So the Cisco inline power is just from Cisco, had about 7 watts of power, and this is at the providing end. That's what the value was there, not at the receiving end. And it ran over 2-pair. Now the same is true with the early power over Ethernet standards from the IEEE. So 802.3 AF and AT both ran over 2 wires, but they provided different levels of power, so 15 watts and 30 watts respectively. And then UPoE and UPoE plus 802.3 BT, way up there, 60 watts and 100 watts, but over 4 pairs. And over here, you can see that we've got our transmit and receive lines, and then we've got our power wires on the other pins. There's 4, 5, 7, and 8. Now down here, this shows you a little bit about how UPoE and UPoE plus combine what's happening on different pairs to get increased amounts of power. So there we go. There's our power over Ethernet, and it becomes really important when you're supporting a campus because you've got, we talk about the Ethernet infrastructure, but there's almost no question that you're going to be supporting wireless connectivity as well. All right, did you know this already? Question number 1. In a two-tier campus LAN design, which of the following are typically true of the topology design? Choose 2. Well, the answers were B and D, that we do a partial mesh between layers and user devices connect at the access layer. That should make sense to you at this point. Question number 2, in a 3-tier campus LAN design, which of the following are typically true of the topology design? And the answer there was A and C. We use partial mesh for access to the distribution and distribution to the core. And of course, we remember that the reason for that is that it's extraordinarily expensive to do full mesh everywhere. But we want some level of redundancy, so we do partial mesh. Question number 3, which one answer gives the strongest match between one part of a typical 3-tier design with the idea behind the listed generic topology design term? All right, so the generic terms were, star, partial mesh, and full mesh, at least for this video. So when we were trying to match up the generic term with the answers that were in this question, the one that matched was D, the access layer looks like a star design. Question number 4, which answers list a criteria typical of a SOHO network? Choose 2 answers. Well, we could have APs in standalone mode, which means that you're not running a controller. You wouldn't have that in a SOHO network. There's no reason for it. And then C, a single device could act as everything, right? That's that wireless home gateway. Question number 5, which answer describes how a LAN switch dynamically chooses the initial power level to apply to an unshielded twisted pair cable with power over Ethernet? And the answer there was auto negotiation. That's the first step for all of this stuff. Question number 6, which of the following refer to standards that deliver power over all 4 pairs in UTP cable? Choose 2. And that was B and D, UPoE, and UPoE plus. Our chapter 14 look ahead is WAN architecture. Well, that makes sense, right? We did LAN architecture. Now we're going to do WAN architecture. And the fun thing that we're going to talk about there is Metro Ethernet and some of the connections, and then multi-protocol label switching. And a little spoiler alert, that operates at layer 2.5. What? I can't even wrap my head around it. We'll talk about some of the basics and then some basic VPN ideas. And then we'll throw in some internet VPNs, right? What are out there? How do they work? And what's good way to look at them and compare them? Well, all right, this has been LAN architecture. In this video, we covered topologies, 2-tier and 3-tier. The 2-tier was the collapsed core. Both of these come from the CLOS topologies. We also visited SOHO topologies. And then we finished up with power over Ethernet, right? There's 4 basic standards that we deal with. Power over Ethernet originals, AT and AF. And then we have the 802.3 BT for PoE, or UPoE plus and UPoE. Well, like and subscribe if you're ready to examine the WAN architecture. And no matter what kind of power you need, may those packets always reach their destinations. We're getting close to the end of this CCNA. You can do this.